Our next speaker is Fermin Olguin. He's a PhD student from our research center here at UPM. His main research interest is modeling and modeling of magnetic components. So we're going to hear something about that. And Fermin, when you're ready.
Good morning, and thank you again for coming to this 7th annual meeting. My name is Fermin Olguin, and I'm going to introduce you the improvements on the design process of magnetic components using PSPR. In this presentation, as an introduction, I will talk about PSPR, and for those that that don't know or are not familiar with the tool, I will talk about what PSPR is and how it can help us to obtain very good designs in very short time. Then I'm going to talk about the improvements on the design using this tool and the new features that will be available soon in PSPR, starting by the losses calculations to the improvements in the simulation step, let's say, in which you can simulate your component in a circuit simulator, followed by a summary of this presentation. Magnetic components are key components in many power electronics applications, but no matter what the application is, magnetics will have losses, and these losses needs to be accurately calculated in the design process in order to avoid the consequences of the miscalculation of that losses that might even compromise the system in which this component will be placed. For convenience, let me divide the design process of magnetic components in 3 steps. The design of the magnetic component itself, in which a component will be configured in terms of number of turns, size, wires, and so on, from a given set of specifications. The modeling step, in which based on calculated parameters such as capacitances or leakage inductance, an equivalent circuit model of the design component can be used to later simulate as a part of an entire system in a circuit simulator. In that sense, we could say that PSPR could be the bridge that the designer can use to get a real magnetic component from those specifications. But what is that bridge? What is PSPR? What is PSPR? PSPR is a complete magnetic component design tool that covers those 3 steps that we have mentioned before, in which a component can be obtained from a specification for electric specification, for example, or a given application, as the case of some power topologies. And it has an extensive library, a database of manufacturers, cores, wires, materials, and offers to the designer many design options that makes the design process more easier and makes the tool itself more versatile. In the modeling step, the tool is provided with a modeler of magnetic components and is linked with a finite element analysis that can be used together, for example, to change some geometrical parameter of a component and see its influence over the behavior of the component itself. Then PSPR allows to simulate the design components in a circuit simulator and to analyze the parasitics, for example, the influence of the parasitics of the design components in the overall outputs, let's say, of our application, in that case, a converter, power converter. Now, this tool can be the aid of the designer to can help the designer to get very robust designs that might be the key, for example, to open the gate of more efficient systems. But now we have an idea about what PSPER is. Let's talk about the improvements that will be available soon in this tool. We know that in magnetic components, losses can be analyzed independently in two different components that are core and winding losses. Let me start by the core losses. There are several ways to calculate core losses in a magnetic component. The most standard one, that is the Stem's equation, is a very simple method, but it's meant to be used, let's say, in sinusoidal excitations in the components. And its parameters are valid only in a limited range of frequency and flux density range. And also, if we have a DC offset, this DC bias is not considered in the calculations. Hysteresis-based method, on the other hand, are very accurate and are valid for any flux waveform, but they have many parameters that are difficult to parameterize. Since the Stem's equation is fast and simple and it only needs 3 parameters, many improvements of this method have been developed in order to overcome its limitations. So let's go back to the Stem's method. If we look at those 2 different examples that correspond to 2 different designs with the same core, material, frequency, but with different excitation, let's say, the maximum flux density in both cases will be the same. So a Stem's equation would give the same value for those different point of operation, let's say. The fact is that core loss is proportional to the rate change of the flux, of the magnetic flux. So we could expect that core losses increase as the magnetic flux change more rapidly. And that is considered in the modified Stem's equation, as you can see in the results, for those cases in which, for example, in the second case, the difference between the modified Stem's equation and the classical statements is more than 40%. This calculation method will be available in future releases of PSPER. Now talking about the winding losses. We know that a magnetic conductor will be affected by an external magnetic field. Well, a conductor will be affected by an external magnetic field. If we place that conductor close to an air gap in a magnetic component, it will be affected by the fringing field, and that means more losses. In an automated design of magnetic components oriented, for example, to losses optimization, which could be the case of any design in PSPER, after the component is defined based on the application and the specifications, the winding loss is calculated in that specific configuration according to one of these methods, typically. If an analytical estimation of the influence of the gap in the magnetic component is not defined in the tool, finite element simulations are required to characterize this component. And depending on the complexity of the component and the number of simulations that we have to run, the design time can be increased considerably. To avoid that, a new option along the options that are offered by PSPER will be included in next releases that take into account all the effects that affect the conductor to calculate the total power losses in the windings of the component. Also, the current capabilities of the model in terms of the modeling will be enhanced in future releases. In this case, the possibility to export a given design to a 3D finite element analysis will be available. That way, we can simulate our component in a 3D environment, and we can get the very most accurate result that we can get from simulations. Also, in electric analysis, the coil and the isolator information is included in the model, and the curvature of the turn is defined in accordance to its distance from the coil. That gives a very realistic model. Also, all PSPR and PMA cores, coils, wires are available for this 3D core modeling. And also, this will be available in future releases of PSPR. In planar designs, the possibility to apply, let's say, advanced winding techniques in planar magnetics, which are important, for example, the interleaving is very important when we want to get a design with very low parasitics. In future releases of PSPR, let's say, possibility, the option to make those advanced techniques will be included, and the results can be evaluated in another window by separate. Another important point in the modeling of magnetic components is the capacitive effect. There are many models that we can use to model these effects in magnetic components, but even if we use the simplest model of the capacitive effects in the magnetic component, the number of required elements to describe with some precision this effect will increase very much when the number of windings in the component grows. And that makes the modeling of the capacitive circuit, let's say, a very, very time-consuming and difficult task. For that reason, a simplified model with a very low number of elements will be available in future release of PSPR to consider or to model the capacitive effects in center tap multi-winding transformers, such as the case of push-pull or half-bridge or full-bridge type transformers. We have seen that PSPR allows us to simulate our design component in a circuit simulator with the entire system. And that way we can see, well, we can have a more realistic simulation and see, for example, the influence of our components in the output voltage, for example, of this converter. We can see the current of waveform in our magnetics and the effect of the parasitic of the magnetics in the circuit. And this is nothing new. You can do that in the current version of PSPR and in previous version of PSPR as well. What is new, what will be new in future releases is that you can run a simulation in your system using, for example, ideal components or desired or approximate components, and take that waveform of the currents and the voltage from the simulation, export that to PSPR, and get a design based on that simulation of that simulated values, and then can use the waveforms in PSPR, make the designs based on that waveform, and then you can go back to the simulator and use the calculated or the design components. Well, as conclusion, a very useful tool with improved calculation methods, the possibility to automatically create a 3D project from the simulation results with improved planar designs and high accuracy simulation models with new functionalities that will allow us and help the designer to get those bulletproof designs that we want to use in our power electronics applications. So that's all. Thank you very much for the attention, and if you have any questions.
Thank you very much, Fermin. We have 5 minutes for questions and answers, so if there is any question, please. Actually, I have one. Sorry.
I have a couple of questions. The first one is regarding the capacitance, because when I saw the presentation, I know that with the capacitive effects I had always several problems.
Yeah.
But I thought that it was not mainly due to the model itself, but in my case I think it's because of the permittivity. Permittivity is not usually provided by the manufacturers with accuracy, and so the capacitance is extremely dependent on that. So
Yeah.
even though the model can be very accurate and you can maybe design a model that really fits the behavior of the device, I think that still there is really work to do with the capacity and permittivity of the materials. Hasn't that changed now, and the manufacturers provide more accuracy on their permittivity data, or is it exactly the same?
No, actually they are the same. We, in that models that will be proposed, that will be included, we try to reduce, for example, the number of finite element simulations that are required to model the component. If you have a component with many windings, you will have, or you will need more simulations, and that means more time. And a way to reduce those simulations and the time for modeling the component is the purpose of this. The information of the permittivity is true that this, well, the model, the calculation is very sensitive to the precision of the given information, of the given data. But actually it is the same. We use the same information because they are already in the database of the PSP.
And I have one more question. It's true that PXpert is focused on the design of the magnetic component, but now there are many commercial devices who you can buy, and you already have a model generator. So are you thinking of including this model generator to generate the model from the measurements of an actual device?
For measurements?
Yes, for measurements of an actual device to include to generate the model and include it in the simulator.
Well, the generation of the model, of the simulation model, is applied to the design components that you can obtain from PSPER. So you use PSPER to design a component. Based on that design, you could get a simulation model. If you have a component, a commercial component that was not designed, let's say, by us and by PSPER, there's, let's say, no need to use PSPER to model that component. You can do that by hand.
But it is to obtain a model valid for the simulator, no? And you have already a model generator in the PXpert,
Yeah.
because the model generator generates the model from some measurements, open circuit test and short circuit test performed in the FEA simulator.
Yeah, it's based on
so
FEA simulation.
You already have the model generator. You could use it to obtain the
Yeah, but in that case, you can model, let's say, your actual component in PMA, which is the modeler of PSPER, but you need to know all the details of that. If you want to use, for example, PMA only for getting a simulation model,
Yeah.
but you have to model with the real geometrical, let's say, characteristic of your component that actually maybe you don't know that.
I was the answer. I mean, the answer is yes, but not in the expert. It will be in a characterization tool that we have
In PMA.
in Simplorer, for Simplorer.
Well, in simpler.
Yeah.
And why not in PSPER?
No, it's
Because
in the
it's a
library.
characterization tool.
From the actual measurement that it
So probably it can be put into both. It's put into both.
is in the library.
Okay, we are running out of time, so Fermin, thank you very much once again.